Hey everyone, and welcome to this explainer. Today we're jumping straight into complete lesson 3.3, all about materials and their structure. We're going to take a pretty mind-bending journey, zooming way in from the everyday physical world we can touch, right down to the invisible building blocks of the universe. Seriously, by the end of this, you're going to look at the world around you in a completely different way.
So, to kick things off, I want you to really think about this for a second. What do an ice cube, a shiny gold ring, and the invisible air you're breathing right now actually have in common? On the surface, right, they seem totally unrelated. One's freezing and wet, one's a solid, heavy metal, and the other, well, you can't even see it. But they actually share a really deep, fundamental connection that makes up literally all of physical reality. And that connection? They are all made of matter. In science, matter is just defined as everything you can see and feel that takes up space. It's literally the physical stuff of the universe. Whether we're talking about a massive ocean, the chair you're sitting in, or even those tiny dust motes you see floating in a sunbeam, if it has volume, if it takes up space, it's matter. Getting a grip on matter is really step one for our top-down exploration today. So, here's our roadmap for lesson 3.3. First up, we'll look at the three states of matter. Second, how matter changes state. Third, atoms and elements. Fourth, compounds and chemical formulas. And we'll wrap up with the magic of mixtures. Let's get into it.
Part 1. The three states of matter: solids, liquids, and gases. You know, scientists sort matter into three main buckets based on properties we experience every single day. Solids, like a brick, for instance, they keep their shape and take up a set amount of space, meaning their volume is fixed. You really can't compress a solid. Liquids, like the water in your glass, take the shape of whatever you pour them into, but they still keep that fixed volume. Try squashing water into a smaller space. It doesn't work. Gases, though, totally different story. They flow and will completely expand to fill whatever closed container you put them in. Their volume can change, which makes them super easy to compress. To understand why solids, liquids, and gases act so differently, we use a really cool concept called particle theory. Basically, all matter is made of tiny particles, way too small to see. In a solid, these particles are arranged in a super tight, fixed pattern. The attractive forces are so strong they can't even move around. They just sort of vibrate in place. That's exactly why solids hold their shape. But in a gas, the particles aren't even touching. There's practically zero attractive force holding them together, so they just zip around freely in all directions. And that is why a gas will just expand to fill a whole room.
Moving on to part 2. How matter changes state, adding and removing energy. Okay, so what happens when we introduce heat? When you heat a solid, you're pumping heat energy into its particles. Step 1, as they gain that energy, the particles vibrate faster and actually take up slightly more space, so the solid expands. Step 2, if you heat it enough to reach its melting point, those particles vibrate so violently that the attractive forces holding that rigid pattern together just break. They start sliding past each other. Boom, your solid just melted into a liquid. And step 3, keep eating that liquid to its boiling point, and the particles get so much energy they completely break free from each other, shooting off into the air as a gas. By just adding or removing heat, we're basically playing DJ to this microscopic dance of particles. To put all this into perspective, think about the Earth's water cycle. It's basically nature's ultimate continuous matter recycling system, and it is entirely driven by those exact state changes we just talked about. Energy from the sun heats liquid water in the oceans, causing it to evaporate into an invisible gas, water vapor. As that gas rises up into the atmosphere, it cools down, loses energy, and condenses right back into liquid water droplets to form clouds. When those clouds get too heavy, the water falls back to Earth as precipitation, rain, or even solid snow and ice. Crazy fact? We're literally drinking the exact same water that the ancient Romans drank. Earth has been recycling this same matter for over 4 billion years.
Part 3. Atoms and elements, the ultimate building blocks.
So let's zoom in even more. Over 2,000 years ago, this brilliant Greek philosopher named Democritus had a pretty radical idea. He thought, hey, if you take a piece of matter and just keep cutting it in half over and over again, eventually you'd hit a piece so tiny you physically couldn't cut it anymore. He called these indivisible microscopic pieces atoms. And you know what? Today, using insanely advanced scanning microscopes, we know Democritus hit the nail right on the money. Now prepare for this because it's kind of mind-blowing. Every single thing you have ever seen, touched, or interacted with in your entire life is made up of atoms. But scientists have found that there are only 118 known unique types of atoms in the entire universe. That's the whole shebang. And honestly, only 94 of those even occur naturally. You can think of these unique atom types as elements. An element is just a pure substance made of exactly one kind of atom, like pure gold, which is nothing but gold atoms, or pure carbon. Think of it like this. Just as the 26 letters of our alphabet can be mixed and matched to write every single book in the English language, these 118 elements combine to make up literally every material in existence. Scientists organize these elemental letters using the periodic table, grouping ones with similar properties together. To keep things simple, every element gets a chemical symbol as a quick shorthand. So H is for hydrogen, O is for oxygen, though sometimes they use the old Latin names, which is why the symbol for sodium is inexplicably Na, short for natrium.
Part 4. Compounds and chemical formulas, building words from letters. While some elements are perfectly happy flying solo, a lot of them love to link up with other elements to form compounds. And this brings us to a massively important concept. When different elements chemically bond to form a compound, they totally lose their original properties and take on brand new ones. Let me give you a wild example. Sodium is a super reactive metal, right? And chlorine is a literally toxic green gas. But if you chemically bond them together, you get sodium chloride. The explosive metal and the toxic gas become completely safe everyday table salt for your French fries. The chemical bond changes the game completely. Because these compounds are such exact combinations, scientists use chemical formulas as a sort of recipe. A chemical formula tells you precisely how many atoms of each element are bonded together in that specific compound. Take the super famous formula H2O. That means you have exactly 2 hydrogen atoms bonded to one single oxygen atom. Carbon dioxide is CO2, 1 carbon, 2 oxygen. Methane is CH4. It's absolutely crucial to get the recipe right, because if you change those tiny numbers even a little bit, you've suddenly got a completely different substance. And finally, part 5, the magic of mixtures, physical, not chemical. This highlights the really stark difference between compounds and mixtures. Remember, in a compound, elements are chemically bonded into a brand new substance, but a mixture, totally different story. A mixture is when you physically mix different elements or compounds together, but they do not react or bond with each other. Because there's no chemical handshake happening, the substances in a mixture keep their own original properties. So if you stir some gray iron filings and yellow sulfur powder together in a bowl, you've just got a messy pile of 2 elements. You could literally take a magnet and pull the iron straight back out of the sulfur because they're just physically mixed. And mixtures aren't just something you do in a science lab. They're absolutely vital for our survival. Seriously, take a deep breath right now. That invisible air you just pulled into your lungs, that's a massive, naturally occurring mixture. It is definitely not a pure substance. When you break it down, air is mostly nitrogen gas, about 78%. Another 21% is the oxygen our bodies desperately need to survive. And that last tiny 1%, that's a hodgepodge of carbon dioxide, argon, water vapor, and some other trace gases. They're all swirling around together in the same room, but they aren't chemically bonded to each other at all. Wow, okay, we have covered a ton of ground in Complete Lesson 3.3 today, going from giant oceans all the way down to microscopic atoms. So I want to leave you with a quick challenge. Look around the room you're sitting in right now. Try applying this new microscopic lens to the stuff around you. What objects do you think are pure elements? Which ones are complex chemically bonded compounds? And which are just physical mixtures? Once you wrap your head around the fact that every single thing you see is just a different arrangement of 118 tiny atomic Lego bricks, the universe starts looking like a much more magical and, honestly, a much more understandable place. Keep wondering about those hidden atomic structures all around you, and I'll catch you in the next explainer.